Hello. Until now, we have focused our attention on the homogeneously broadened active media. Now, let us look at the inhomogeneously broadened active media. And this comes with its own complexity because you see, what you have is a collection of identical atoms to begin with. But given the specific physics underlying the collection of atoms, for example, we are looking at the velocity degree of freedom for a gas, or in case of solid state laser, we are looking at the variation in the location of the active atoms doped within the background crystal matrix. So all of these lead to identical atoms turning different. Their central frequencies, which is their resonant frequencies, are slightly shifted because of the physical phenomena underlying the inhomogeneous broadening. Let me look at it a little pictorially. So imagine I have a collection of atoms, and this is my gain spectrum. And you know that the gain spectrum, this is an inhomogeneously broadened gain spectrum. So the central peak corresponds to the location nu 21, which is the resonant frequency associated atom. But because of inhomogeneous broadening, you see that spectrum is arising out of a collection of independent spectra, right? These are different atoms which are having, you know, their own, for example, central frequency. So even though we began with identical atoms, a statistical collection of all these now different atoms because of inhomogeneous broadening is actually leads to the spectra that we are talking about. So keep this picture in mind, and because that is what underlies the inhomogeneous broadening. In contrast, in the homogeneous broadening, right? So this I am calling as inhomogeneous broadening. In the homogeneous case, what you have is what you have is a spectrum which is identical for every atom. So this spectrum is identical for the whole collection of atoms, right? Uh, so let's look at the notion of saturation pictorially. So you see that if I'm looking at saturation and imagine that my laser frequency nu L, which is oscillating in this range, so you see that this frequency is in resonance with a specific collection of atoms, which is within that homogeneous broadened line width, but centered at nu L. It is only these atoms that will see this radiation on resonance. The rest of the atoms, because they are slightly displaced, will see this radiation to be completely out of resonance. And hence, the interaction between these other sets of atoms with this frequency will not be sufficient for the transition to get saturated, right? So what would happen that in a inhomogeneously broadened system, you would have the you will have the original line shape, but now you'll see that here there is a saturation that happens. My original line shape has now transformed with a hole in the gain, right? Because of saturation, the gain actually decreases. This decrease is only confined to the atoms which are on resonance, right? It is only these atoms that um, get saturated. In contrast, in a homogeneously broadened system, so for example, this again is my the central frequency nu 21. I could be anywhere, right? But the whole spectrum gets saturated for every set of atoms because you have a homogeneous collection of atoms. So you see, this is the difference, the contrast between inhomogeneous broadening and homogeneous broadening. Now one may ask, for example, what is the width of this spectral hole that we have burnt in this gain profile? This width will be, let me call it delta nu. Let me call that delta nu, and this width is actually the homogeneous line width associated with that collection of atoms and centered at nu L, right? So this becomes now the width of the hole that one has burnt. Not just that, the depth of the hole depends on the intensity of the lasing radiation within the cavity, as we have seen in our previous lecture. So this hole could be deeper, it could be shallower, and so on. So for example, another level of intensity within the cavity might give you a shallower hole. So the extent of the hole would depend on the intensity. So let me write that out. So the depth of the saturation hole is depends on the intra cavity intensity. The location, by location I mean the spectral location of the hole, right? It depends on the laser cavity frequency. The laser cavity frequency nu L might be different from nu 21, right? Which is the average collection of atoms and their central frequency. So for example, in Doppler, these are the nu 21 bar is the collection of atoms which have zero velocity components along the direction of propagation, right? So the new laser might be different from that, hence the hole appears at a different place. Of course, if the laser is tuned to the central frequency, in that case, the hole will appear at the center, right? So that is what one is talking about. And the width of the hole, please remember we are talking about a hole in the spectrum now. The width of the hole is simply dependent on the homogeneous line width of the corresponding atoms within the, let me call this as a spectral packet. So the spectral packet is centered at nu L and the width is delta nu, right? So that is what one is. So this is what makes the collection of atoms to be inhomogeneous in one case, and the collection of atoms being homogeneous, the whole dynamics of the process of saturation is completely different, right? So now let's concentrate a little bit on the Doppler broadening specifically. This particular effect that we are going to talk about, which is the spectral hole burning, in the Doppler broadened case was actually envisaged, discovered, and experimentally realized by Lamb. So you recall the Doppler phenomena that we have discussed in one of the lectures earlier. And what you have is you have the stationary atom has got a frequency, for example, nu to 1 bar, and this stationary atom's resonant frequency is seen by the light as different. So this is the stationary atom resonant frequency. V is the velocity of the atom, and you see that nu 21 is the shifted frequency as seen by the light of this particular atom. So you see that this essentially distinguishes depending on the value of V by C. What you see is that you get these nu 21 minus nu 21 bar. This is the shift in the frequency space that you actually observe. All right. So, so the velocity is mapped to a frequency shift within the within the spectrum. There is a certain symmetry that we need to invoke within the cavity. So, for example, this is my cavity, and I see that my a wave that is traveling that way. Imagine there is a collection of atoms which is traveling that way, right? This is a collection of atom with the velocity ratio v by c, and this is the frequency nu L that is traveling to the right, right? Imagine that in this situation, this particular collection of atoms is on resonance. That is, so if I'm looking at in the spectral domain, this is my nu 21 bar, and my that is the one which is the largest number of atoms, right, situated there. But because of my nu L is not on resonance, so it will be on resonance with a particular set of atoms within this spectral packet about nu L. This is traveling with a velocity, let's say, v by c. If these set of atoms are in resonance with nu L, there is a exactly equivalent set of atoms that is traveling backwards. So this is, let's say, if this was minus v by c, this is plus v by c, right? And there is, of course, the backward traveling field, which is exactly of the same frequency nu L, right? So you see that if this combination happens to be on resonance, right, clearly there is a equivalent combination which is between this field and these atoms. They are exactly equivalent but traveling exactly the opposite way. So you will see that because of this, right, there is going to be another group of symmetrically placed shifted atoms which have got a velocity, uh, you know, which is exactly equivalent and negative of that one. So if I call this set as arising out of the collection which is at plus v by c, this is a set that is arising out of the collection minus v by c, right? And these are equivalent. So what you would see is the following, that because of the symmetric existence of these collection of atoms, you would see that the gain curve is actually saturated symmetrically about the central frequency. So this I am saying is the effect of saturation in Doppler broadened media, because you see you have an equivalent collection of atoms going the in the other direction. So now as you tune your laser, so the next step is, let's say I tune the laser radiation, right? How do you tune the laser radiation? By changing essentially the length of the cavity, because you know that the length of the cavity specifies the frequency that is supported. So if I tune my nu L such that it matches with the nu 21 bar, so you see that these atoms in my figure here, these atoms were actually talking to independent collection of atoms, equivalent in number but independent collection of atoms, right? Now these two collection of these two different spectral wave packets were addressing different set of atoms, and as you tune them, you would see that both of these dips or the spectral holes come closer and closer, and you would find that at resonance, you would see that now, let me draw it with another color. So at resonance, as you're tuned, you see that you'll get a central dip, and this central dip is going to lead to a lowering of the intensity, because now rather than looking at two separate spectral packets of atoms, you're looking at the same collection of atoms, and hence the saturation is more, and there is a dip in the intensity, and this particular dip is what is called as the Lamb dip. So Lamb actually predicted this, and this was observed. In the Doppler broadening case, you have the spectral hole being symmetrically placed about the resonant central frequency. And as you tune the laser to the central frequency, you see that there is a reduction in the gain, uh, and you get this central dip, which is known as a Lamb dip. So remember that this is actually a effect arising out of the standing wave pattern with the two counter-propagating fields. And the distribution of active atoms is symmetric about velocity distribution is such that it is symmetric about that central collection. This business of a hole being created in the gain profile is what is known as spectral hole burning. Because of saturation, one has burnt a hole within the cavity at a hole being created in the spectral domain. This is called as the spectral hole burning. Contrast this with the spatial hole burning that we talked about, wherein it is the physical location, spatial location of the atom and the spatial location of the nodes and antinodes of the standing wave pattern that led to burning of holes in the spatial gain profile in contrast to this situation. Let me again qualify. For the red curve, you have nu L, which is not equal to nu21 bar, whereas for the green curve, you have nu L equal to nu21 bar. So let us keep that in mind. So this is our discussion on the spectral hole burning in contrast to the spatial hole burning that we had looked at earlier.